Physics part 308, we talk about the example here and we get to the question C. The mass of the moon is 7.4 into 10 power raised to 22 kilogram. Calculate the gravitational attraction between the earth and the moon. Gravitational constant G is equal to 6.7 into 10 power raised to minus 11 Newton per meter kilogram square. Now it's your turn. The mass of Jupiter is 1.9 into 10 power raised to 27 kg and its radius is 7.1 into 10 power raised to 7 meter. Calculate the gravitational field strength at the surface of Jupiter. Gravitational constant G is equal to 6.7 into 10 power raised to 11 Newton per meter per kilogram. Mass and weight. Well, mass was said to be a measure of the inertia of a body to changes in velocity. Unless the body is traveling at speeds close to that of the light, its mass is constant. In gravitational field, by definition, there is a force acting on the mass equal to the product of the mass and gravitational field strength. This force is called the weight. For an object of mass m is in a gravitational field of strength g, the weight W is given by weight is equal to mass into gravitational field strength, or W is equal to mg. Although mass is invariant, weight depends on gravitational field strength. For example, a person of mass 60 kg has a weight of 600 newtons on Earth, but only 100 newton on Moon, although the mass is still 60 kg. Gravitational potential energy and gravitational potential. We met the topic earlier of electric potential energy and electric potential. There is very strong analogy between electric and gravitational fields. This is going to help us when we talk about gravitational potential energy and gravitational potential. Gravitational potential at a point in a field is defined as the work done in bringing unit mass from infinity to the point. The symbol for gravitational potential and its unit in the joule per kilogram, JKG, for a field produced by a point mass equation for the potential of a point in the field. Note the minus sign. This is entirely constant with the electrical case. We had a negative electrical potential when the field was produced by a negative charge, so that the force between the negative field or producing charge and the positive test charges are attractive. Here the attractive gravitational force between the field producing mass and test also gives us negative potential. We've got an example how much work is done by the gravitational field in moving a mass m of 2 kg from infinity to a point A, 0.40 meter from mass m of 30 kg. The work which would have been done by an external force is simply the change in the gravitational potential energy. The potential energy at infinity is zero. So we've got an equation here. This is the work which would be done by an external force and is negative. So the work done by the field is positive and is equal